That's a true statement. There is gravity data over the whole world. The National Geospatial Intelligence Agency, NGA, in the U.S. has a world gravity map, and you can get an appreciation for what the gravity is around the world to a certain level. A lot of that was collected with the shuttle systems, the shuttle radar altimetry program. A lot of it is just a compilation of gravity collections that have been done around the world, marine surveys or land surveys for different things. So it's true, there is a worldwide gravity database. The problem is that it's generally not high enough resolution for areas of specific interest. So if you're looking to target, here we are in Texas, if you're looking to target fields out in West Texas, you would really need to do some local gravity surveying and find out, what are the characteristics there, or anywhere else you want to look, which is why there are still needs for active gravity data collection programs. National scale sometimes to be used in advance of letting tenders or licenses out for different properties. Smaller scales, once you've identified, this is a prospective region and you want to get a better information of what the subsurface geology is. So there's a great gravity database. In many cases, though, it's not sufficient. The challenge is, as I mentioned earlier, the fact that targets that we're looking for today are smaller, are deeper, are not in necessarily traditional locations that we might expect to find hydrocarbons or minerals. So I can see that there will be a need for better resolution and better performance from sensors, particularly if we're going to be looking for more minerals. As we approach what you might call the green revolution and the focus on renewables and so on, we're going to need to extract from the earth more minerals to satisfy that objective than we have extracted to date in human history. I mean, the needs for, specialty minerals, copper and silicon, and lithium and cobalt and rare earths and all these things, the quantities that we're going to need are just massive if we're indeed going to make this transition away from fossil fuels. So there will be a need for more surveys. There will be a need for higher resolution surveys. It's really been exciting to see the airborne transition of what were marine gradiometer systems. The airborne environment is much more difficult. The turbulence, the dynamics are really tough to overcome, and it took a really strong team effort to be able to do that. I guess another one would be another application of gradiometry outside of this space is it was used for arms control verification purposes for the Defense Nuclear Agency. The story on that is that there were a number of international arms control treaties, and they had inspection technologies that were going to be deployed to validate that these treaties were being honored. People weren't cheating. And so one of the things that we looked at was using a gravity gradiometer to inspect rail cars as they come out of a production facility, either in the US or in this case in Russia. And so we did a whole series of tests down at Kirtland Air Force Base in New Mexico in the mid-1990s to validate that we could actually identify and characterize items that were sealed inside of a boxcar and know what configuration it was, if it was a nuclear armed weapon or if it was a conventionally armed weapon, simply by looking at its mass distribution profile. This was a really exciting project. And so what was exciting about it was we took this lab equipment, that's normally under very nice conditions, and brought it out into the field and set it up and, drove trucks through portals and did all kinds of neat measurements. And it was incredibly successful from a technical perspective. It was a failure from a political perspective because the requirement of the treaty was that we had to give the same technology that we had to the other country. Well, that wasn't going to happen. So the reciprocity requirement of that treaty protocol, but we went 3 or 4 years doing that program. It was really a lot of fun. I ran that program, and the technical success was amazing.
Yeah, I don't know that I have a lot or that I can add a lot, but I did get involved a little bit. And, there's a paper that I was a co-author on from one of the guys at Mines back, I don't know, in their 2010 to 2015 timeframe. But I was involved some on some work with gravity, with sequestration, and using gravity to track the, doing the sequestration work and things like that. And there seemed to be some positive things out of that. So, I can see the application of gradiometry and detailed gravity to help some of these things. I think the biggest problem I see is people accepting it. Like I said, I thought there could have been a lot more done at Prudhoe Bay with the work we did. John Siebert in particular did a whole bunch of work to get things, the location information, which was almost as important as the gravity, as far as being very accurate to do this work. And we did all this work and repeat surveys, and they never really bought into it enough to continue to do those surveys and use them to the extent that I thought they should. And I thought we saw some of the similar things with the sequestration work that we did. But I don't know where that's gone, because I kind of left before that got too far. But from that kind of work, I can see the impact gravity could have, detailed gravity could have in some of these things like geothermal and so forth. But, clearly magnetics can be done in highly detailed, it's very accurate. Slew of places that the companies acquired data and then didn't do anything with it. I'm like, you spend $500,000 collecting a really good survey, and then you won't spend, you won't spend more than a few weeks or a few months interpreting it and incorporating it into your data. I mean, even within the companies I worked for, from office to office, you saw that impact. You'd collect a gravity survey with an offshore seismic survey, and they'd collect gravity data because they just tacked it on, and then they wouldn't do anything with it because the particular office, the guy that was in charge of exploration, didn't believe in gravity or whatever. So, you had to get a buy-in from some of these people. And especially in the later years, Corinne, you came from a contractor standpoint, so you were always in the contracting. But, in the later years, probably the last 15 or 20 years of my career, there was we actually acted as internal contractors. So if the particular office didn't want to pay for our services, it didn't matter if they had lots of data, it just sat there. I could be sitting in my office doing nothing, but if they didn't want to, they wouldn't let me do anything with their data, because if I did anything with their data, they had to pay internal dollars. I obviously spent my career doing it, and I think it never was used as much as it should be.
I believe that potential fields has got a wonderful future, and that we will succeed, and the young people will have a career. Gravity and magnetics, I have to blow the bugle for them, because they are not the most expensive method to put in a database. I mean, they are reasonable. It's a product that will help you find oil and gas and minerals, whether it's used as the number one, item. But most people, as you know, Corrine, and as you know, Julianne, they go ahead and put it together and get as much data as they can, because that's what it's all about, is to have the data. And you've got geophysicists and such, as you know, you've got to have something for them to work with. And so you can get down to a skeleton crew, but when things come around again, I think that gravity is going to be one of the first things that they'll look at. That's crazy, but you talk reconnaissance tool. That's what a lot of companies use it for. A lot of the majors go in, and before they enter an area, they're going to get gravity, and if magnetics look good to them, they'll get it also prior to spending money on seismic, etc. And it is a first step for the companies. And I'm seeing that that's just the way it's been used by majors. Now, I have clients that are they're currently looking into areas in East Texas and in other areas, conventional plays and such that are, and also the shale plays. But it's kind of a toss deal there. It's
I think there's a future for gravity measurements. It's going to continue. It's not just for oil and gas, but for geohazards, archaeology. Some of archaeology has not got a lot of money chasing it, so you can't spend too much money on expensive technology for some of the more interesting applications that there are in the world.
Well, in the last couple of decades, the oil and gas utilization of gravity has migrated from land gravity to airborne gravity. But in that same time, mining exploration has continued to predominantly use land gravity. I think there's maybe a higher realization of its usage and its benefits. But our business initially started out as a 50-50 arrangement between oil and gas work and mining, possibly a little thrown in. Now it's predominantly, almost exclusively mining. Certainly been an interesting career. Been to an amazing number of places. I'm in the process of transitioning out of day-to-day operations, and the younger guys that are taking over have the same enthusiasm getting into it as possibly I did 40 years ago. They don't need me to sell them on it. They're pretty enthused and they're pretty excited about taking over and seeing where this goes for them.
Yeah, I think the next step forward will not be in the gravity instrument itself, but in adding other instrumentation into the aircraft so that we have a more accurate measurement of the position of the aircraft and the accelerations that the aircraft is undergoing. I think the airborne geophysics business is great for young people who are just graduating. It allows a lot of travel if they're interested in travel. It is a technical business, and it also gives young people a lot of It gives the young people a lot of responsibility early in their career. They can go to the field and be in charge or be involved in a project that's costing a lot of money every day. So it's important to get good results every day. And I think when it's done properly, people are very proud of the work they do, and it can give them, they can come away from a project feeling great. So I think that's one of the things about airborne geophysics is that the teamwork to get a project going is really important. But at the end, it feels good that everybody's done their part and the project has been successful.
So one of the interesting parts of gravity survey technology that's adapting and improving as we go into the future here is the use of high-tech modern digital elevation models. We've always had a really strong pillar of gravity surveying with the actual instruments, with the LNRG meter and the more recent LNR alloy meter. And over the past couple decades, we've gone into kind of the GPS era and away from land surveying. And so the positional survey has moved into the future with absolutely reliable GNSS surveying. The third pillar of gravity surveying, especially for exploration, for mineral exploration and for small targets, is to refine the elevation model of the area. In the past, that was a bit of a liability on the gravity side because pre-elevation models, we would have to use manual terrain corrections using inclinometers. In the modern era, we can either fly our own digital elevation model using UAVs, you can purchase them from satellite providers, or you can use government-provided DEMs. And it really refines the process and takes away the only liability that gravity surveying had in extreme topography. I think it's a very dynamic industry. It's you get to see all sorts of interesting places and do all sorts of interesting things, and I think there's a lot of upward potential.
I think that there's going to be more and more gravity being acquired in locations that are difficult, and certainly large regional surveys will be flown with gravity on an aircraft with gravity gradients. So there'll always be a need to collect gravity data. Gravity is very important to measure for any mining or petroleum company. The change of densities in the ground beneath you are measured with gravity meters, and that is critical to any sort of resource exploration. And the other thing that gravity meters will tell you is, for instance, you can measure voids in the ground, so you can detect the presence of cavities. The French used gravity in front of all the road crews when they were building roads in the 1960s to measure just cavities that would form and prevent their road crews from actually falling into sinkholes as they built the roads. Gravity will always be important for resource exploration. So whether you're looking for petroleum, whether you're looking for minerals, gravity measurements will be important. Land gravity measurements, just taking simple measurements along the ground in the survey will be done, and pretty well every project out there. But in the future, and what's happening is that gravity meters have been moved onto aircraft and into boats and to the bottom of the ocean. So more and more gravity is now being measured in environments that we could not reach by doing land gravity surveys, simple land gravity surveys. And now they have developed instrumentation that actually measures vertical gravity gradients from an aircraft. And I must admit, I do not understand how that equipment works. I was a skeptic when it first came out, and I said that'll never work, but it does, and it sees the geology, and and I still don't understand why it works, but it's truly an amazing instrument. I'm very keen on measuring gravity in a borehole. So we've taken that. While I was at Centrex, we took the sensor and we shrunk it down, and we put it into a little ball. It's heat control, and it's smaller than a golf ball. And then we can put that into a sonde that we can lower down into a borehole, and we can take gravity measurements much closer to the source. Now, the difficulty there is understanding the data, because all of a sudden you've got sources all around your meter instead of only below your meter. So interpreting the data is a challenge, but I think there's a big future in collecting gravity in a borehole for things like monitoring, sequestration monitoring, or identifying areas for carbon mineralization. Or the other thing that is going to be used a lot for gravity is just simple monitoring change. If you put a gravity meter on the surface, an absolute gravity meter is very good for this. You can take an absolute gravity measurement at a location on the Earth, and you can come back a year later and you take that exactly same location. You can measure glacial rebound of 4 millimeters. So a 4 millimeter change in the elevation will be detectable with gravity meter. Well, an absolute gravity meter is going to be used by people who want to really study gravity. So absolute gravity meters you find them in metrology labs, around the world, and they're actually studying gravity as opposed to using the tool as a device for exploration. So you'll see absolute gravity meters in metrology labs and people who really want to study gravity. The other use for absolute gravity meters is in monitoring. And one of the big success stories for absolute gravity meters was in Prudhoe Bay. They were able to use an absolute gravity meter on an annual, come back every year for a series of years, and to be able to see and monitor a water flood. They were injecting water into a formation about 8,000 feet beneath and they were able, using gravity at the surface, absolute gravity meter, to actually detect and map where the water was actually going after it had been injected.
Yeah, there's some pretty interesting things kind of out of the world of science, and often these come out of the university labs. Things like atomic interferometry, AI as we refer to it, superconducting technologies are pretty exciting. Some new work that's coming out of Western Australia that is pretty neat, looking at ribbon sensors and string sensors that have some advantages from its form factor. For example, it could go down in a borehole, and the fact that it's a fundamentally simple measurement as opposed to having to use, cryogenics and so on. But there's quite a few systems under development and in the pre-prototype and even in the lab demonstration phases that use superconducting capabilities. Silicon Microgravity gave a talk recently at the SEG meeting, the image meeting here in Houston, and talked about their silicon MEMS gravimeter, which is pretty exciting. There are other groups out there that are developing similar things. So you see universities like Stanford or University of Cambridge or Oxford or University of Glasgow or others in Europe and across the world that have spent a lot of time and effort focusing on these fundamental physical capabilities and principles. So there's neat stuff like that on the horizon. Whether or not it will be practically deployed, they still face a lot of the same challenges of, getting an instrument to work is one thing. Getting it to work, in a dynamic test in a lab is another thing. Getting it to work in a deployed vehicle like a plane or a ship, even harder. But I think that there's hope. A lot of the things that will probably be in place 25 years from now have not even been conceived and are still at the stages of, fundamental physics or fundamental science to be able to develop them. Well, you have to have good data, but once you have good data, you have to be able to handle data and you have to be able to process it appropriately. So there have been incredible improvements in noise reduction, in data integration. That's kind of a key theme in my view, is integration, because you can have, perfect magnetic data, perfect gravity data, whatever it might be, but yet you're going to even do better if you can enhance it, if you can integrate it with additional measurements. So kind of my vision, if you will, for the future is a platform or a capability of bringing together all of the significant geophysical measurements, magnetics, gravity gradiometry, electromagnetics, maybe in appropriate cases, radiometrics, certainly with improved LiDAR, which is terrain measuring capabilities. Improvements in GPS will help all that. Bringing that all together. Now you've got all this good data, but how do you integrate it? That's going to become a challenge, but yet we see a lot of improvements and advances in things like machine learning, in artificial intelligence, and the application of being able to handle large data sets. I've seen recently some visualization capabilities that are really stellar, that can take in very large data profiles from multiple sensors and be able to integrate them together to come up with a solution. So I think that there's a lot of work to be done on that end, a lot of opportunity on that end, and I see that's going to be a big part of what happens in the future. I would encourage them to pursue, from an engineering perspective, challenging projects, because, who wants to just do the same old, same old? When I started working with what was then Bell Aerospace in the mid-'80s, became Lockheed Martin, we were on the cutting edge of doing something that never really been done. We can actually deploy a gravity gradiometer on a submarine or on some other vehicles and measure these sort of levels of fidelity. How are you going to do that? It was an incredible technical challenge. And it's really fun to work with a team. I'm a mechanical engineer by training, but the electrical engineers and the software engineers and the people that are skilled in all these different disciplines, I think it's incredible. And I would encourage somebody to pursue, if you want to work for a company that either makes instrumentation, or if you want to work with a company that actually takes this data and does exciting things with it, I found it very fulfilling.
Well, you asked me what my philosophy was one day, and I have to say that it's a must. I've always believed that it's a must to know where you come from, to be able to progress. And as an interpreter, you have to know where the data came from and what happened to the data before you get it and you interpret it and have a vile confidence in your interpretation. And so what I hope is that people will be able to see where these instruments came from, how they came about, the ones they're using today. Okay, that's my hope, is that they'll get to understand that. Where they came from, why did they come, how come, who put so much time in them, and now I'm using it today.